notice, and this is the typical copyright. We continue with mathematics syllabus for CSEC 2018 to 2027. Schedule of videos. Section 1, Number Theory and Computation. All 33 of those videos have been published as of 14th of October 2024. Section 2, Consumer Arithmetic. All 12 of those videos have been published on YouTube in their entirety as of 17th of November 2024. Sets, 6 videos, and this is the first of these 6. Then by December 2024, end of December, measurement. January 2025, statistics. February 2025, algebra. March 2025, relations, functions, and graphs. April 2025, geometry and trigonometry. And finally, by May 2025, mid-May, hopefully vectors and matrices. Section 1, Number Theory and Computation. This is just a reminder that Section 1, I have divided into 33 videos, and all of those have been published on YouTube in their entirety. The reason for that is that this section forms the foundation on which the rest of the syllabus is based. How well you can handle this section, that is Section 1, will predict how well you will be able to do with the rest of the syllabus. So please look at those 33 videos first from Section 1. Reminder also that you need to know the times tables from 2 to 12. And then Section 2 had 12 videos. Those 12 from this section plus the 33 from the previous section, Section 1, should be 45 videos from Sections 1 and 2 have all been published on YouTube in their entirety. Now we go to Section 3, sets. This that you see here is a print screen from the syllabus. There are 4 objectives here, and you do have explanatory notes for all 4 of them. Then there are some more objectives here, 8 of them in total, and that would be all the objectives in Section 3. So there aren't that many objectives in this section, and I can combine objective 1 and 2 into one video, which is this one, first video. And then there is video 2 and video 3, video 4, video 5. Objectives 7 and 8 can also be combined into one video, which will be video 6. So in total, this section has only 6 videos. Only the first 3 will be made available in their entirety on YouTube. Only the first 3 up to there and upwards. The other 3 will be partially available on YouTube as notification if you are subscribed to this channel. If you want to see them completely, you will be redirected to another site where a reasonable subscription fee is required. So we begin here, which says explain concepts relating to sets. And just in case you cannot see the writing here because it is too small, in larger fonts, examples and non-examples of sets, descriptions of sets using words, membership of sets, cardinality of sets, finite and infinite sets, universal sets, empty sets, complement of a set, and subset. So those are the things we will look at first in this video, objective 1. We can also deal with objective 2 in this same video, which says represent a set in various forms. Represent a set in various forms. And then it gave the 3 forms that you are required to know. As a description, as set builder notation, and listing all the members of the set. So that is what we will be doing in this video. So let's begin with objective 1, explain concepts relating to sets. We will begin this section by referring back to section 1 of objective 1. That would be the very first video in the mathematics series. We defined a set as a well-defined collection of things without regard to their order. And that is taken from the syllabus. It's a definition from the syllabus, page 67. So if you are going to learn a definition of a set, learn this one. Recall from number theory, when we did section 1, objective 1, distinguish among sets of numbers. Now, there are various ways to subdivide any group of somewhat similar entities based on specific characteristics. One of the simplest everyday examples is pets. The most common subdivision of pets would be dogs and cats. But then dogs can be further subdivided into large dogs and small dogs. And then large dogs can be further subdivided into various breeds of large dog. For example, Great Dane, Saint Bernard, Burmese Mountain Dog, German Shepherd, Alaskan Malamute, Doberman, just to name some of the most popular ones. This can be done for any large group of items or entities as long as there is some specific characteristics. Example, people, fish, trees, microbes, programming languages, computers, and so on. And it can be done for numbers too. The groups may not be exclusive. Sometimes there is an overlap. Still on recall, work that we already did. Distinguish among sets of numbers. This was section 1, objective 1. Talks about the various sets of numbers, natural numbers and whole numbers and integers and so on. And then, continuing that, sets of numbers. Still recall, we talk also about irrational numbers and terminating and recurring decimals. And then we talked about real numbers. So this is work that we already did. And this is a summary of numbers and their various sets and subsets. So if we take all real numbers, we can divide that into 2 larger subsets. One will be Q, which would be the rational numbers, and the other one would be F, which would be the irrational numbers. Under the rational numbers, you have fractions that are terminating or recurring. You have integers, whole numbers, and natural numbers. Now, let's get back to this objective, 3.1. Explain concepts relating to sets. First of all, we will talk about examples of sets and examples of non-sets, and also membership of sets. So we will define these things before we go on to use them. A set is a collection of distinct, well-defined objects of the same kind forming a group. It is normally represented by an uppercase letter. Example, M is the set made up of males in grade 10 in XYZ school. Or F is the set of females in the finance department of PQR company. They are well defined and they are related. Now, any group of items in which the members or the elements are not well defined is a non-set or is not a set. For example, if I say F is a set of fat males in grade 10, or if I were to say S is a set of short females in grade 9, here are some questions you need to ask because it's not well defined. What do you mean by fat or short? Who determines that? So it is not well defined. And so this here, F here, is not considered a set and neither is S. Now, an individual item in a set is called an element or a member of that set. So 4 is a member or an element of the set E, which is made up of 2, 4, 6, 8, 10. That is, 4 is an element of E. This means an element of. 8 is also an element of E. However, 3 is not an element of E. As you could see, E does not contain 3. And neither is 12 an element of E. So we have looked at those terms, examples of set, of non-sets, of members. Now let's look at cardinality, finite and infinite sets. A finite set is one in which all its elements can be listed. Now, if E is the set of all even numbers from 1 to 20, then E is the set 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So all the elements can be listed. If M is the set of all grade 10 students in XYZ school who were born in the month of March, then M could very well be the set made up of Peter, Carlos, Scott, Martin, Teresa, Nicole, Angelique, Hannah, and Julie. It's finite. You can list all the members. Conversely, an infinite set is one in which its elements cannot be all listed. For example, if E is all the even numbers greater than 9, then E will be the set 10, 12, 14, 16, 18, and you could go on forever. All the elements cannot be listed, so that would be an infinite set. If S is the set of all stars in the universe, then S would be star 1, star 2, star 3, star 4, up to how many billions of stars. We cannot list them. So that would be an infinite set. Now the cardinality of a set, now that's a big word, don't let that fool you or scare you, is the number of elements in that set. So it's very simple, written as N of E. That is to say, if E is a set 2, 4, 6, 8, 10, up to 20, how many elements do we have in that set? Then N of E is 10, or the cardinality of the set E is 10 members. I'm not too sure why they use such a big word, cardinality, when all they mean is the number of members in that set. However, please learn that that is what cardinality of a set means. If M is a set made up of Peter, Carlos, Scott, Martin, and so on, Julie, and so on, then the cardinality of M, the number of elements in the set M, is 9. You count those students there, and you get 9. So cardinality is the number of elements in the set. Now, if you find this video useful and interesting, please like and share. That is to say, like and share. You may also consider subscribing to this channel. Subscribe. It doesn't cost you anything and it means a lot to me. Now, in this slide, we are going to look at description of sets using words. And we will come back to that in the next objective. Now, just now, when we were talking about a finite set, we said it is one in which all the elements can be listed. For example, E is the set of all even numbers between 1 and 21. Notice we described the set. Or we could say M is the set of all grade 10 students in XYZ school who were born in the month of March. Again, we describe the set. So we already did this in the last slide when we were talking about E and M here. Just the name of the set followed by a word description. No equal sign and no braces, no brackets. So that's one way of describing a set using words. And we will look at that again in the next objective. Now we are going to look at universal set and subsets. For any particular situation or problem, the universal set is the set that contains all the elements from which subsets can be extracted. It is denoted by the uppercase U. For example, if the problem involves only whole numbers from 1 to 20, inclusive, then the universal set would be 1, 2, 3, 4, 5, right up to 20, from 1 to 20. No other number can be considered in this situation or in this problem. Whatever question is asked, your answer is restricted to the universal set. A subset exists only within the domain of a universal set. Any part of the universal set is a subset, and a subset is indicated by this stretched, somewhat looking C. So if E is the set 2, 4, 6, 8, and so on right up to 20, and U, which is the universal set, is made up of the whole numbers from 1 to 20, it can be seen that all elements of E are found within U. Therefore, E is a subset of U. You can find E within U. If E are the even numbers from 2 to 22 inclusive, and U is that universal set we had up there, 1 to 20 inclusive, it can be seen that all elements of E are not found in U. There's a problem with this 22 here. Therefore, E is not a subset of U. Here is a definition from your syllabus. Subset of a given set is a collection of things that belong to the original set. For example, the subsets of uppercase A are A, B, AB, and the null set. And we'll talk a little more about the null set just now. That is taken from your syllabus, page 67. It's a definition for a subset. So right now, we will be talking about empty set. The empty set is a subset that has no element in it. Now, it is indicated by this symbol here. It's an O with a stroke across it. Or a set symbol without anything in it. This is a special case and may not seem logical or reasonable at first glance. For example, consider the universal set 1, 2, and 3. There are many obvious subsets that can be easily listed. For example, 1 by itself, 2 by itself, 1 and 2, 2 and 3, and so on. Now, what is not so obvious is that if all these elements were removed, we would still have a subset, but now it has nothing in it. Hence, the empty set or null set indicated by either one of these symbols, it is accepted set theory, even if it does not seem reasonable to us. Consider it as a special case. You will understand it better when we deal with intersection of sets later. Related to that is the other special case. And in this case, the complete universal set is also considered as a subset. Hence, the set 1, 2, 3 is a subset of the universal set, which is also 1 to 3. Again, this is accepted set theory, even if it does not seem reasonable to you. So it looks like U is a subset of U. Lastly, in this objective, we will talk about complement of a set. Now, if U, which is a universal set, the elements are 1, 2, and 3, then the odd numbers can be represented as a subset O, which would be 1 and 3. So 1 and 3 is a subset of U, or O is a subset of U. Now, what elements or elements is missing from the subset O? But it is included in U. Obviously, the answer to that is 2. So we can state that as E is equal to 2, even numbers, in that universal set. Note carefully that subset E has elements that is or are not part of the subset O, but included in the universal set. E is therefore said to be the complement of O, of course, within U. So the complement of the subset O, written as O prime, is the subset of all other elements in the universal set that are not elements of O. So O prime is equal to E, or O complement is equal to E. To summarize, if U is the set 2, 3, 4, 8, and 9, and P is the subset 2, 8, and 9, 2, 8, and 9, then what is left is P complement, which would be 3 and 4. Just to be clear, when the universal set is Peter, Carlos, and Julie, and S is Peter and Carlos, then S complement, or S prime, is Julie. If the subset Julie is represented by D, then S prime is D. So some of these concepts may be made clear when shown in a Venn diagram that we will learn about later in this section. This is a preview right now, dealing with these concepts that we just talked about. So let us say you have a box like this, and in that box, we have the universal set, which is made up of whole numbers 1 to 20, inclusive. So those are the numbers in the universal set, 1 to 20. Now we want to separate a subset E, which is even numbers, from this universal set that we have on the left here. So if we draw an oval like that and call it even numbers, obviously you have some numbers in there that are not even, and you have some numbers outside that are even. So we will need to move any element not in its right place. So let's start moving 5 out, 3 out, 13 from there, 7 from there, and then move in 8, 14, 10, 20, and 18. Looks like we now have all the even numbers from 1 to 20 inside this yellow oval here. So that's even numbers. and the odd numbers on the outside. So those odd numbers, E prime, will be the complement of the subset E, all within the universal set of whole numbers 1 to 20. So we finish that. Now we will deal with objective 2, this, in this same video. Represent a set in various forms. We already looked at one. Description, that's this one here. The set A comprising of the first 3 natural numbers. So you can describe a set. 2, or B, set builder notation. This one is a little harder to understand, but we will look at it in detail. And C, listing, as A is a set of numbers 1, 2, and 3. You list all 3. So that is what we will be doing here. We already know this one and that one. This one here may pose a little problem. So description, it must be concise, precise, and unambiguous. You must not be able to ask, what does that mean? Or does this include such and such? C, listing. A is a set of numbers 1, 2, and 3. Now, that's 2 ways. The third one, as I said, could be a bit confusing. Set builder notation. It is somewhat tricky. A symbol is used to represent the element. In this case, the symbol is X. Then a colon, followed by the range of X. And finally, X is a member of what group? So you would read that as A is the set of all X such that 0 is less than X, which is less than 4, while X is a member of the natural numbers N. That is how you would read that. That is one way to read it. A simpler and a more understandable way could be this. A is the set of all X such that X is greater than 0. So instead of reading from going this way, we start here and we change this less than to greater than. And so we say X is greater than 0 and it is less than 4. That is easier to understand, while X is a member of the natural numbers N. All natural numbers between 0 and 4. That is 1, 2, and 3. That is what it means. Before we go on, just a reminder about the meaning of these symbols: less than, greater than, less than or equal to, and greater than or equal to. Notice in this set builder notation, you have less than and less than here. Now, many learners often confuse less than and greater than. Now, here is one way to help you remember which one means greater than. And of course, if you know which one means greater than, then the other one means less than. If you sit at a desk, here is a desk, with a book in front of you, and this is you looking down from the top, that's your head. Consider the shape of your right arm as you view it, that is, view your right arm. It bends somewhat like this shape, with the elbow pointing to the right, like this. Now, if you are right-handed, your right hand or arm is greater to you than your left. That is, it is more important to you. So if you are right-handed, this is very easy to remember. This sign here that has the shape of your right hand, which is greater to you, means greater than. So 9 is greater than 5. Now, for the few of you who are left-handed, maybe 15%, then you have to think in terms of all the right-handed people who outnumber you, because those are about 85%. I don't know how that will help the left-handed people, but I know it will help the right-handed people. So we will next consider 5 examples of representing a set in various forms. 5 examples. Example 1. Description. The set P comprising of the first prime numbers. That's one. So it's concise, precise, and unambiguous. That is not open to misinterpretation. And of course, you could list all the elements of the set A, which would be 2, 3, 5, 7, and 11. That's very easy. The other one, set builder notation, is the set P of all x such that 0 is less than x, which is less than 12, or x is greater than 0 and is less than 12, where x is a member of prime numbers. So what it really means is all prime numbers between 0 and 12. That is what it means. Now, I am sure if you see the set builder notation, you would be able to understand it in terms of the other two ways of expressing it. Problem is, if you see the other two ways and you have to set it up as set builder notation, that is where the difficulty may lie. Example 2, this is the description. The set E made up of even numbers between 1 and 21. Now, it doesn't include 1 and it doesn't include 21. So it's concise, it's precise, and it's unambiguous. And of course, that would be E is a set made up of these elements, 2 to 20. They are even numbers between 1 and 21. Okay, now let's look at the set builder notation. The set E of all x such that 1 is less than x and x is less than 21. Or, as I said, you can start from the middle here, where x is greater than 1 and less than 21. And of course, x must be a member of even natural numbers. So as I said, this one is a little harder to do given the other two. But given this one, it is fairly easy to convert it into the other two, because it's really all numbers between 1 and 21 that are even natural numbers. Example 3, description. The set I made up of integers between -5 and +6. Between them, not inclusive. Again, concise, precise, and unambiguous. But then you can list them out like this. Set I, if it's between -5 and +6, then you begin at -4 and you go up to +5. All elements are listed. Now, set builder notation. Again, I is the set of all x such that -5 is less than x, or you could say x is greater than -5 and x is less than 6. X is a member of integers. Example 4, description. The set G made up of even numbers between 6 and 16, excluding 6, but including 16. Again, as I said, concise, precise, unambiguous, not open to misinterpretation. So G is the set of numbers. Now we will exclude 6. So we begin at 8, 10, 12, 14, but it says including 16. So that's very easy to understand. All its elements are listed. Now, set builder notation. G is the set of all x such that x is greater than 6. X is greater than 6 if you look at it that way. Or 6 is less than x, while at the same time, x is less than or equal to 16, x is a member of even natural numbers. Example 5, the set V is made up of vowels of the English alphabet. That's a description. I'm emphasizing it must be concise, precise, and unambiguous. There may be a little problem here, but we will look at that at the end. But normally, this should not pose a problem to most people. So if you list out all the elements of V, it would be A, E, I, O, U. All its elements are listed. Now the set builder notation, again, V is the set of all X such that X is the vowel in the English alphabet. So X are the vowels in the English alphabet. Now I know there may be some people who do a little advanced English and they may say, well, you leave out Y. All right, normally we don't count Y as a vowel. It's a special case. So we will leave it out for now. Example 6, the description M comprises all students in grade 12 at XYZ school who were born in the month of March. Okay, again, concise, precise, and unambiguous description. It is not open to misinterpretation. Of course, you could list all the members of M, and let us say those were Peter, Carlos, Scott, Nicole, Angelique, Hannah, and Julie. All the elements are listed. Now, if you use a set builder notation, you could say that M is a set of all X, such that X would be the student's name, and X would be a member of grade 12 students in XYZ school born in the month of March. So we began here at this objective 1, explain concepts relating to sets. We explained that. And then we did this objective here, 2, as well, represent a set in various forms. As a matter of fact, 3 forms that CXC lists here. 3 forms. And that brings us to the end of this video, which is video 1, based on objectives 1 and 2 in section 3.